Auzubillahiminash-shaytanir-rajim. Bismillahir-Rahmanir-Rahim. Dear student, Assalamu alaikum. Today we are going to start the topic 7.6, which is Archimedes Principle on page number 155. Class 9, subject physics, chapter number 7. We are doing properties of matter. Topic of today's lecture is 7.6, which is on page number 155. And pages covered we will today 155, 156, and 157 pages we will try to cover. I repeat, class 9, subject physics, chapter number 7, properties of matter, and topic of today's lecture is 7.6, which is on page number 155. And we will try to cover the other pages as well, 156 and 157. This is a chapter we are doing, Unit 7, Properties of Matter, and today's topic is 7.6, Archimedes Principle, on page number 155. Page number 155. Please open 9th class textbook, page number 155. We are covering today 7.6, Archimedes Principle. Before understanding Archimedes Principle, I will try to give you some example uh, before starting this Archimedes Principle. These examples are based on the same principle of Archimedes Principle. An air-filled balloon immediately shoots up to the surface when released underwater. This is the first example. The same would happen if a piece of wood is released underwater. You must have noticed that the stone feels light underwater but feels heavy as soon as we take it out of the water. So he took the example of an air-filled balloon. You have noticed that when the air-filled balloon is dipped under the water, what happens if we release our force? The air-filled balloons come at the surface of the water. This is just because when upthrust force is acting on the air-filled balloon. Similarly, same thing happens when we apply the force and try to dip the uh, wooden piece of wood under the water. And when we release our hands force, what will happen? The same thing happen as the air-filled balloons comes on the surface of water. Similarly, the piece of wood also comes to the surface of water when we release our uh, hand force. So you might also have noticed that whenever the stone you must have noticed that the stone feels light underwater but feels heavy as soon as we take it out. So the stone in when we dip in inside the water, it is light, and when we take this out from the water, you feel uh, it feels heavier than it was in the under the water. So these are the three examples on the Archimedes principle. So the definition of Archimedes principle is now I'm going to read the definition of Archimedes principle. When an object is totally or partially immersed in a liquid, an upthrust force acts on it equal to the weight of the liquid it displaces. Who gave this definition? More than 2000 years ago, the Greek scientist Archimedes, his name was Archimedes, he gave a he defined the upthrust force. Okay, so more than 2000 years ago, the Greek scientist Archimedes noticed that there is an upward force which acts on an object kept inside a liquid. As a result, an apparent loss of weight is observed in the object. The upward force acting on the object is called the upthrust force of the liquid. Archimedes' principle states that he noticed that whenever the object is dipped under the water, an upthrust force of water. That upthrust force is what? Upthrust force is the water force, which is water is applying on the object whenever the object is partially or fully immersed into the water. Immersed mean when it is dipped into the water. Okay, so there is an upward force act on the upthrust force acts on the object whenever the object is placed inside the whenever the object is dipped inside the liquid. This upthrust force is this gave the concept by Archimedes principle. So he said that if there are the two containers, one is the bigger one, you can see in the figure 7.10. So whenever this is an object which is going to be dipped, this one which I am pointing out, this is the object which is going to be immersed or which is going to be dipped into the water. So what will happen? We apply the force on the top and it will go into the dip into the water. This is the force, F2 is the force which is acting in opposite direction to the object that is called the upthrust force, which is which gave the idea by Archimedes principle. Archimedes gave the idea whenever the object is placed inside the water, whenever the object is dipped inside the water, an upthrust force, which is F2 force, is acting on the object, which uh, which react in the opposite direction. Okay, this is the force. This is the force which we applied to dip the water inside the liquid, but this is the force which the water is applying on us. Okay, so this object is fully immersed into the water. So we can calculate the height as well, depth as well. So H1 is the depth from the bottom of this liquid to the top of the first container, and H2 is the depth from top of the container, top of the bigger container to the top of the smaller container. So H2 is the height depth of the container from the top surface to the top surface of the smaller container. And H2 is the height from top of the surface, water surface to the bottom of the smaller container. So these are the two heights. If we want to calculate the difference of the height, how we can calculate the difference of the height? H2 minus H1. H will be H2 minus H1. Okay. Consider a solid cylinder of cross-sectional area A. So this is a solid cylinder of cross-sectional. Its area is capital A. You can see this is the capital A area of this smaller container. Consider a solid cylinder of cross-sectional area A and height h immersed in a liquid as shown in figure 7.18. Let H1 and H2 be the depth of the top and bottom faces of the cylinder respectively. H1 is the top and H2 is the height of the bottom faces of the cylinder respectively. So how we can calculate the difference of the height? So in order to calculate the difference of the height, so you can subtract this H2 minus H1, you can calculate the small h. So let if P1 and P2 be the liquid pressure at depth H1, P1 is the liquid pressure at depth H1 and P2 is the liquid pressure at depth H2. There are the two pressures, two heights, two pressures. So P1 is the pressure, liquid pressure at depth H1 and P2 is the liquid pressure at depth H2. And you can calculate the density, and density, you know, the density form, density is noted with rho, as we had discussed in our earlier lecture. Then according to the equation 7.3, you have already studied in 7.3. 7.3 figure is on page, equation is on page 152. If you open page number 9th class textbook, page number 152, P is equal to rho GH. In my earlier lecture, I derived this P is equal to rho GH. Pressure is equal to rho GH. On page number 152, equation 7.3. We use same equation to calculate the pressure for depth H1 and the pressure P2 for depth H2. So if we want to find out the pressure P1, so our equation will be 7.3 equation will be rho GH1. But if we want to calculate the pressure on depth H2, so P2 equals to rho GH2. So there are the two pressures, P1 is equal to rho GH1 and P2 is equal to rho GH2. So these are the two pressures we calculated by using the equation 7.3, which is on page number 152. Let the force F1 be exerted on the cylinder top by the liquid due to the pressure P1, and the force F2 be exerted in the bottom of the cylinder by the liquid due to P2. As I have already told you, F1 is the force which we applied to dip the solid cylinder into the water, and F2 is the force which is a reaction of the force or exerted, which is the upthrust force acting on the solid cylinder by the water. So there are the two forces F1 and F2, and there are the two pressures P1 and P2. Okay, so we calculated the pressures P1, which is rho GH1, and P2 with rho GH2 by using equation 7.3 on page number 152. So, so our formula will be, so we know the formula, pressure is equal to force per unit area. We know the formula is pressure is equal to force per unit area. So if we want to calculate the F1, so that will be P1A, and F2 is equal to F1 is equal to P1A, and F2 is equal to P2A, because you already have studied the pressure formula. Pressure is defined as force per unit area. Pressure is defined as force per unit area. So using that formula, I calculated F1 and I calculated F2. F1 will be P1A and F2 will be P2A. So since we calculated the two pressures, P1 is equal to rho GH1 and P2 is equal to rho GH2. I'm just going to put these two pressures in the equation number in my pressure in these equations. If I want to find out the pressure F1 force, so P1 multiplied by A. So P1 value is rho GH1 and A will be as it is. So if I want to find out F2, that is P2A, I use this formula and substituting the P1 and P2 pressure respectively. First of all, I use P1 is equal to rho GH1 and P2 is equal to rho GH2. I'm just putting these two pressures in the equation. F1 is equal to P1A and F2 is equal to P2A. So P1 is equal to rho GH1. I just put P1 equal to rho GH1, and A will be as it is, and F2 is equal to P2 times A, and P2 is rho GH2 times A. So since we have two forces, so if we want to calculate the difference of these two forces on the net force, then we will subtract this. So F2 minus F1 is the net force F on the cylinder, is called the upthrust of the liquid. Okay, so I subtract this F2 minus F1. So F2 is, this rho GH1A, and F1 is rho GH1. So if you can calculate rho GA common from these two, so rho GA is common here and rho GA is common here. So if you subtract this rho GA, so what is left with H2 minus H1. So H2 minus H1 is equal to H. As I have already told you, H2 minus H1 is equal to H. H2 minus H1 is equal to H. So rho GA is equal to H2 minus H1. H2 minus H1 is H. So A, when area is multiplied with height, as I have already explained you in the last lecture, when area is multiplied with height, it is equals to volume. So my upthrust of a liquid will be equals to rho GV, rho GV, where here AH is the volume V of the cylinder and equal to the volume of the liquid displaced to the cylinder. So therefore rho GV is the upthrust of the liquid displaced. Equation 7.6, this is the equation number 7.6, shows that an upthrust force acts on the body immersed in a liquid and is equal to the weight of the liquid displaced, which is Archimedes principle. So my Archimedes principle equation will be rho GV. My Archimedes principle equation will be rho g v. I explain again. We have two cylinders. I'm going to study Archimedes principle, and this is the definition of the Archimedes principle, and these are the examples of the Archimedes principle. I gave you the examples of air-filled balloons when it is dipped into the water, and when we lift our force from the air-filled balloon, it comes on the surface of the liquid. It comes on the surface of the water. So this is an example of, because there is a upward force acts on the air-filled balloon, which keeps the object, which keeps the air-filled balloon on the surface of the balloon whenever the applied force is lifted. So when an object is totally or partially immersed in a liquid, an upward force acts on it equal to the weight of the liquid it displaces. So for this, we consider two cylinders. So one is the bigger cylinder and one is the small solid cylinder. And the area of the small solid cylinder is noted with capital A. And F1 is the force which is used to dip the solid object into the water. And F2 is the reaction force which is the which the water is applying on the solid cylinder. So if we consider two heights, there are the two heights H2 and H1. So H2 is the height from the top of the solid cylinder, bigger solid cylinder, to the bottom of the small solid cylinder. H2 is the height. And H1 is the height from the top of the bigger cylinder to the top of the smaller cylinder. If we want to calculate the difference of these heights, H2 is greater than H1. So how can we calculate the difference? Difference can be calculated with the H2 minus H1. So therefore, we calculate H2 minus H1 is equal to H. So P1 is the pressure on the depth H1, and P2 is the pressure exerted height H2. So I calculated the pressure rho GH1 from the formula. We use 7.3, equation 7.3 on page number 152. If you open page number 152, we discussed equation in our last lecture 7.3. I use this formula to calculate P1 and P2. So P1 is calculated as rho GH1. P1 is at height H1, depth H1, and P2 is at depth H2. So I calculate the pressure P1 is equal to rho GH1 and P2 is equal to rho GH2. Similarly, F1 is the force top force, and F2 is the force which is water is getting on the solid cylinder. F1 is my hand force which is used to immerse the solid into the liquid, and F2 is the force by the water on the solid object. Similarly, I use this formula F1 pressure. Pressure formula is pressure is equal to force per unit area. If I want to find F1 force, so F1 will be P1A and F2 will be P2A. I use this formula. So formula is pressure is equal to force per unit area. I use that formula to calculate F1 and F2. And then I just put the values. P1 is equal to rho GH1 and A will be as it is. I use this formula. P1 is equal to rho GH1 and P2 is equal to rho GH2 in this equation. In these equations. So P1 is my rho GH1 and P2 is my rho GH2. So then I calculate if I want to calculate the net force or the upthrust force acting on the object, so I will subtract F2 minus F1. My F2 is rho GH1A or my F1 is rho GH1. So if we take common from these two, so rho GA can be taken as common. So what is left inside? H2 minus H1. So I know H2 minus H1 is equal to H as I have calculated here. So H2 minus H1 is equal to H. So that's why I'm substituting H2 minus H1 is equal to H. So H2 minus H1 is equal to H. So we have calculated AH when area is multiplied with height. So that is equal to volume. So our upthrust force of liquid will be rho GV. So 7.6 is the upthrust force of the liquid. So I will use this formula to calculate the upsurge force, which is rho gv, where rho is the density, g is the acceleration due to gravity, and v is the volume, which is called upthrust force. So, student, I'm going to discuss now example 7.3, which is on page number 156. This example has come in a board examination to 2018 group 2. So I read the numerical statement, example statement first. A wooden cube of size 10 centimeter each has been dipped completely in water. Calculate the upthrust of water acting on it. So we will use this formula to calculate the upthrust force. I told you rho GV or equation 7.6 is the upthrust force of liquid. We will use this formula to solve the example 7.3. First of all, I write the given data. Length of side is 10 centimeter. So first of all, we convert this into meter. So 10 divided by 100 is 0.1 meter. So since in this equation we have volume, so volume has three lengths. That's why I'm taking a cube of the lengths, because volume has three lengths. 0.1 multiplied by 0.1 multiplied by 0.1, we have 1 into 10 power minus 3 cubic meter, and the unit of volume is cubic meter. And you know the density of water, rho is equal to 1000 kilogram per cubic meter. This is understood uh, value of the density of water. You should know by heart. Rho is equal to 1000 kilogram per cubic meter. This is the density of water, which is understood value, which you need to memorize. Length is 0.1 meter, and since in this equation we have volume, so volume has three lengths. That's why I'm multiplying three times. 0.1 multiplied by 0.1 multiplied by 0.1. If we multiply this, 1 into 10 to the power minus 3, and the unit of volume is cubic meter, and the density of water is rho, which is 1000 kilogram per cubic meter. So since I want to, in this formula, calculate the upsurge force, I want to calculate the upsurge force in this example. So I use this formula rho GV. And rho is the density of water, which is 1000, which you got to remember. And G is 10. Value of G acceleration due to gravity is 10 meter per second square. And volume is 1 into 10 power minus 3. If you multiply this with the help of calculator or solve by hand by yourself, minus 3, minus 2, minus 5, and how many zeros? 1, 2, 3 times power 3, minus 5, so minus 2. So if you solve this, you will get 10 Newton force. That is the upthrust force, which we just found. We just calculated the formula equation for the upthrust force, which is rho GV. I use this formula rho GV to calculate the upthrust force. So the upthrust force, water is acting on the liquid on cube is 10 Newton. So this is the upthrust force, uh, which is the which we calculated using this formula rho GV. Now I'm moving towards the next thing, which is 157 on page 157, density of an object. Density of an object. Before this studying this, I give you the we have already done this experiment in the lab. So we calculated the weights over here. These are the two weights. So a stone is attached, and this stone is in the air, and this stone is dipped into the water. So what will happen when the stone is in the air? Its density is more, but whenever the stone is dipped into the water, its density will be less. Its density will be less. You can see this. So Archimedes principle is also helps to determine the density of an object, because Archimedes principle is used to find the density of different objects. The ratio in the weights of the body with an equal volume of the liquid is same as their density. So suppose density of the object is denoted with capital D, and density of the liquid, or in this case the water density, is rho, and weight of the object is denoted with W1, and weight of the equal volume of liquid is W is equal to W1 minus W. So we have to, this is a stone, where this is in air and this is in when dipped into the water. So how can we calculate densities? By using this formula, the ratio of the density of the object to the ratio of the density of the liquid, the weight W1 divided by net weight, W is equal to W1 minus W. So this is the formula. If you multiply it, rho is multiply here, divide here. If it is go on the other side, it will be divide. So capital D is the density of the liquid, density of the object we can found with the help of this formula. D is equal to W1 divided by W1 minus W2 multiplied by rho. Rho is the density of the liquid and capital D is the density of the object. So there is a difference between these two densities. This capital D is the density of the object and rho is the density of the liquid. That's why they are of different symbols. D is capital D is density of the object and rho is the density of the liquid. So use this formula. So we calculate the densities of the objects. So in this case, as I have already told you when we discussed this, as I have already told you, whenever the object is placed under the water, it feels light. Stones. You have must have noticed that the stone feels light under the water, but feels heavy as soon as we take it out of the water. Similarly, we will discuss this. It will be light when it is go under the water, and it will be heavy when it is on the air, in the air. It is not dipped into the water. Here, this is in air. Stone is in air, but here the stone is in when dipped into the water. It feels light when it is inside the water, and it feels heavy when it is outside the water. So I use this formula to calculate the density of the object because Archimedes principle is used to find the density of the different objects. Now I am going to discuss example 7.4. The weight of a metal spoon in air is 0.48 Newton. Its weight in water is 0.42. You can see this. The weight is in air is 0.4 Newton. It is more, but when it is dipped into the water, the weight is reduced, which is reduced to 0.42. From 0.48, it is in air, and when it is dipped into the water, the weight is reduced, which is 0.42 Newton left. So find the density. So weight of the spoon in air is 0.1. Weight of the spoon in air is denoted with W1, which is 0.48 Newton, and weight of the spoon in water W2, which is 0.42 Newton. And density of water, you know, we use this, the liquid is here is water, and water density is 1000 kilogram per cubic meter. But we need to find out density of the spoon. In this case, I will use this formula density capital D is equal to W1 divided by W1 minus W2 times density. So capital D is equal to, I use this formula, which is 7.7. I use this equation. D capital D is equal to W1 divided by W1 minus W2 times rho. So W1 is 0.48 and W2 is 0.42. So I use this equation. D is equal to capital D is equal to W1 divided by W1 minus W2 times rho. Rho is the density of water, and density of water, you know, is 1000 kilogram per cubic meter. And the weight W1 is 0.48 and W2 is 0.42. So if you subtract this, W1 is 0.48, W1 again 0.48 minus W2 is 0.42. If you solve this, if you subtract this and solve this, you will calculate the density of the spoon, which is required, which is 8000 kilogram per cubic meter. So I repeat example 7.4. The weight of the metal spoon in air is 0.48. As I have already told you, whenever the object is dipped into the water, it feels light, and whenever it is in air, it feels heavy. That's why the metal spoon in air, the weight of the metal spoon in air is 0.48 more, and weight of the water in when it is dipped, when it is immersed, that is left to be 0.42 Newton. So it is less than this one. So when it is dipped, its weight is reduced 0.42, and when it is in the air, it is 0.4. I use, and you know the density of water is 1000 kilogram per cubic meter. Use this formula. This formula D capital D is equal to W1 divided by W1 minus W2 times rho. So W1 is 0.48, W1 is 0.48, and W1 again 0.48, and W2 is 0.42. Multiply by rho is density of water, which is 1000. Just plug in the values here, and when you solve this, 0.48 minus 0.42, subtract this, and then divide this 0.48 divided by this value, subtraction value, and multiply with 1000 with the help of calculator. You will find the density of the stone is 8000 per kilogram per cubic meter. So density of the material of the stone is 8000 kilogram per cubic meter. This is my result. So this is the end of the topic. Today's topic, Archimedes principle. I hope you understand this topic very well. If still you have any problem regarding this topic, please let me know and feel free to ask the questions. Thank you. If you have any questions, students, regarding this topic, I can ask questions. And you have, you need to memorize the topic covered in today's lecture. I mean to say, Archimedes principle by heart and write them once on the rough registers. So you need to practice this today's topic on the rough registers. This is your homework. Thank you. If you have any questions, please let me know. Yes, in homework, I told you already, you need to show me only the numericals on the neat registers. This is for your practice at home. So you need to, the, the, the topic we covered every day, whenever we have the lecture, you need to memorize this by heart, right? And for your practice, try to solve it and try to do it on the rough register for your practice. I will not check your rough registers. I will check only the neat registers, which are MCQs and which are numericals. I need to check whenever the chapter will finish. When we will solve the problems, at the end of the problem, we will solve the problems. I will check that only. Only there I will check those things. But I will not check this one, the rough registers. This is for your practice at home. Anyone has any question? Usman, Zuhair, Ibrahim, anyone has any questions, please let me know. मेहरुनिसा, अगर आपको आज के लेक्चर में कोई प्रॉब्लम है तो आप पूछ सकते हैं। आज कोई चीज कोई समय ना लगी हो तो बताएं। उस्मान, मुजना, प्लीज। कोई चीज आपको समय ना लगी हो